Hello everyone. Today we will explore a very interesting paper presented at FSC 2020, and it is titled as Fuzzing on the Exponential Cost of Vulnerability Discovery. In this work, the authors examine a fundamental question in cybersecurity. What is the true cost of discovering new software vulnerabilities? In this presentation, we will look at the underlying economics of automated bug discovery and discuss how the findings challenge common assumptions about scaling security efforts. The paper encourages us to think critically about the resource allocation and efficiency in the pursuit of stronger software security. We will also highlight several counterintuitive insights that carry important implications for both practitioners and researchers. To begin, let us first establish a clear understanding of fuzzing. So let us begin with a brief overview of fuzzing. It is a technique that has become a cornerstone of vulnerability discovery. At its core, fuzzing involves automatically supplying a program with random inputs to observe how it behaves under unexpected conditions and to identify potential failures or security vulnerabilities. The fuzzing process typically starts with the seed corpus, which is a collection of initial inputs that are known to be valid or interesting. These seeds serve as the foundation for exploration. The fuzzer then performs mutation, systematically modifying or generating variations of these inputs to create new test cases. Each mutated input is subsequently passed to the program during the execution phase, where the program runs while the fuzzer monitors its behavior for crashes, hangs, or anomalous responses. A key component of fuzzing is the feedback loop. Coverage-guided fuzzers collect runtime information such as which code paths were executed and use these feedback to prioritize inputs that explore new areas of the program. And this iterative process enables the fuzzer to intelligently navigate complex software and discover previously hidden vulnerabilities. And the effectiveness of fuzzing is well demonstrated by large-scale industry efforts such as Google's continuous fuzzing initiatives, which have uncovered tens of thousands of bugs across critical software systems, including Google Chrome, and numerous open-source projects. Modern fuzzers are also inherently non-deterministic and highly scalable, that allows them to operate across extensive computing infrastructures. However, this raises an important question. If fuzzing is so powerful, what happens when we simply add more computational resources? Does increased scale always lead to more vulnerability discoveries? We'll examine this apparent paradox. So this brings us to the central puzzle this paper solves, the scalability paradox. It is a counterintuitive phenomena where adding more machines can make vulnerability discovery both faster and surprisingly slower. Imagine Google scaling its fuzzing infrastructure by 100 times. On one hand, finding the same known vulnerability becomes exponentially faster, which means you can rediscover bugs in a fraction of the time. But here's the catch. Finding new, previously unknown vulnerability becomes exponentially more expensive, as you can see on the plot on the left. Each new bug requires a disproportionately larger investment of resources. So the more bugs you have already found, the harder it gets to find the next one. And this paradox forces us to rethink how we allocate resources in security. If you had an unlimited budget, would you invest in more machines or in smarter fuzzing algorithms? We'll explain this into the research why this happens. So to investigate this paradox, the authors conducted an ambitious study, one of the largest of its kind. In total, they dedicated more than 4 CPU years of computation to fuzzing nearly 300 open source programs using tools such as libfuzzer and AFL. A CPU year represents the amount of processing work a single computer processor would perform if it ran continuously for an entire year. In practice, this workload can be distributed across many machines running in parallel. For example, 4 machines running for 1 year each, or dozens of machines running for shorter periods. This highlights the scale and computational intensity of the study. And the researchers aim to answer three fundamental questions. First, how does increasing the number of machines influence the discovery of additional vulnerabilities? Second, how does scaling computational resources affect the time required to uncover the same vulnerabilities? And third, what is the relationship between computational scale and the probability of finding a specific set of vulnerabilities? In this context, the number of machines serves as an abstraction for the rate at which a fuzzer can generate and execute test inputs. More machines effectively mean more test cases being produced and evaluated per unit of time. And by systematically varying this rate, the authors analyzed how scaling inputs impacts vulnerability discovery. And this setup allowed them to derive empirical laws that describe the economics of fuzzing. Let's begin with the first key finding. The first empirical law reveals a fundamental truth about vulnerability discovery, and that is finding new bugs is exponentially expensive. It states that even if a non-deterministic fuzzer generates exponentially more inputs per minute, it discovers only linearly more new species, whether those are vulnerabilities or just unique code features. Think of it like collecting baseball cards. The first few cards are easy to find, but as your collection grows, finding that last rare card becomes progressively exponentially harder. Similarly, to find linearly more bugs in the same time frame, you need exponentially more machines. For instance, if you want to find a new bug within 24 hours, you might need to double your machine count. And this law highlights the diminishing returns of simply throwing more hardware at the problem and searching for novel vulnerabilities. But what about the bugs that are already known? Let's explore that in the next law. So finding new bugs is expensive, but the second empirical law offers a more optimistic view, which is rediscovering known bugs or covering existing code paths is actually quite cheap. A non-deterministic fuzzer that generates exponentially more inputs per minute discovers the same number of species exponentially faster. This means if you double your machines, you can find the same bugs in half the time. For example, running libfuzzer on 512 machines instead of just one reduces the time to find the first crash from nearly 6 hours to under a minute. And this has huge implications for continuous integration. You can fuzz many targets for short periods and cover a lot of ground very quickly, but it also highlights a pitfall in fuzzer evaluation. Simply comparing fuzzers based on coverage achieved in X hours can be misleading. A small increase in coverage might hide an exponential cost in resources. Now let's explore how the probability of finding a bug changes as we scale our efforts. So the third empirical law describes us how the probability of discovering a specific vulnerability changes with computational resources. For a non-deterministic fuzzer, this probability increases exponentially until discovery is expected. Then the rate of increase slows down, and the curve approaches probability 1. We call this the sigmoid discovery curve. Think of it like a threshold effect. Below a certain number of machines, the probability of finding a specific bug is near zero. But once you cross that threshold, the probability shoots up rapidly, then plateaus as you approach certainty. This means adding a few machines might do nothing if you are below the inflection point. You need enough resources to climb the cliff of that sigmoid curve. And this law helps us understand why some bugs are so elusive, even with significant resources. But why do these three laws hold true? And the answer lies in the underlying distribution of vulnerabilities, which we'll explore next. So To truly understand why fuzzing behaves this way, we need to delve into the species model, which helps us grasp the distribution of vulnerabilities. In fuzzing, a species isn't a biological term. It refers to a unique program behavior, a distinct code path, or a specific vulnerability that can be triggered by an input. Software contains a vast diversity of these potential bugs. Some are shallow, easily found, and frequently triggered, while others are deeply hidden and require very specific, rare inputs. This diversity isn't evenly distributed. The frequency of these species follows a power law, meaning a few are very common, but the vast majority are extremely rare. This creates what we call a long tail of hard to find vulnerabilities. So when we talk about finding new bugs, we are often talking about exploring this long tail, which inherently becomes more difficult as we exhaust the common species. This concept is crucial for understanding the exponential cost we've been discussing. And it sets the stage for our next analogy, which further clarifies this challenge. The species model helps us visualize the distribution of bugs, and now we can apply a classic mathematical analogy, the coupon collector's problem. This problem asks how many trials, like buying cereal boxes, are needed to collect a complete set of unique coupons. The formula shows that the expected number of trials grows superlinearly, approximately n times the natural log of n. This directly explains why finding the last few bugs becomes exponentially harder. Each unique vulnerability or code path is a coupon, and each fuzzer input is a trial. Imagine you have found 18 out of 20 unique bugs. The next input is very likely to be a duplicate of an already found bug, making the search for those last two extremely inefficient. This analogy perfectly captures the diminishing returns we see in fuzzing. It's not that the bugs don't exist. It's the probability of hitting a new one decreases dramatically as your collection grows. And this mathematical foundation underpins the empirical laws we have discussed, and it provides a robust explanation for the observed exponential cost. These empirical laws have profound implications for how we approach vulnerability discovery in practice. Some security experts like Khalid Yaghtan, Hank Pauli, and Andrei Konovalov suggest simply throwing more CPU power at fuzzing isn't the most effective strategy. Instead, we need smarter approaches. For CI/CD pipelines, this means fuzzing many targets for short periods rather than one target for a long time. You'll quickly find that low-hanging fruit, but when evaluating fuzzers, we should compare them based on the time it takes to discover the same bugs, not just the coverage achieved in a fixed time. And critically, this research and development investment should focus on algorithmic efficiency, better seed selection, smarter mutations, and new feedback signals. And these small improvements can yield exponential gains in the long run, shifting that expensive curve in our favor. Like every study, this study also has its boundary and limitations, and understanding them helps us apply the findings correctly. So this paper makes some simplifying assumptions that are crucial to acknowledge. The biggest assumption is that adding more machines perfectly translates to generating more inputs, with no overhead. But in the real world, especially with grey box fuzzers, machines need to talk to each other. If they don't share information efficiently, like discovered seeds or coverage, you lose a lot of that scaling benefit. Without smart synchronization, your 32 grey box fuzzers might not be much better than 32 black box fuzzers. So while the empirical laws hold under ideal conditions, real-world fuzzing needs careful engineering to get close to those theoretical limits. Here's a question. What other factors might affect fuzzing scalability that this study doesn't capture? Now let's put this work into perspective. Fuzzing has been around for decades, evolving from simple random testing to the sophisticated coverage guided techniques that we use today. But for all that evolution, one question remained largely unanswered. How does fuzzing scale? Previous research often focused on making fuzzers better, asking how do we find bugs better? But it shifts this paper shifts that focus entirely. It's the first systematic study to investigate the economics of scalability, and it asks what's the return on investment for adding more machines. And this work fills a significant gap by moving beyond just technique improvement to a fundamental cost benefit analysis. And this brings us to our conclusion and what this all means for the future of vulnerability discovery. So what's the big picture here? This paper gave us three empirical laws that fundamentally change how we think about fuzzing. First, finding new vulnerabilities is expensive. It takes exponentially more resources. Second, rediscovering known vulnerabilities is cheap. More machines mean exponentially faster finds. And third, the probability of discovery follows a sigmoid curve, meaning those last few bugs are incredibly hard to reach. The core insight is clear. Retesting is cheap, but finding truly new vulnerabilities is expensive. And this leads us to critical future directions. We need smarter seed selection, better feedback signals beyond just coverage, and hybrid approaches that combine fuzzing with other techniques. Ultimately, the question isn't whether to scale, but how to fuzz smarter, so that the exponential cost curve becomes more favorable. Thank you.